All right, I think we can start. Welcome everyone to this week Autonomy Talks. This week is a great pleasure to have with us Dr. Giuseppe Belgioioso, who is a postdoctoral researcher at the Automatic Control Lab here at ETH Zürich, also working in the CCR. Something about Giuseppe. So he received his bachelor degree in information engineering and master's in automatic control engineering, both at the University of Padua. And then he moved to the Netherlands, where he obtained his PhD degree in automatic control at the Eindhoven University of Technology. During his studies, he also visited Arizona State for a while. His research interests include the game theory, operator theory, and distributed optimization. And in particular, he focuses on studying and solving coordination, decision, and control problems in complex network systems. Today, he's going to present some results that allow one to construct feedback controllers for complex dynamical systems to bring these systems to nice equilibria, or socially efficient equilibria. Clearly, this has a lot to do with the things we are interested at in the Autonomy Talks, and that's why we are all very happy to hear the talk. And with this, Giuseppe, the stage is yours. I think you're muted.
Thank you very much, Joelle, for the very kind intro, and also for the invitation. And also thanks a lot for all of you for taking the time and follow this talk. So the main motivation for this work, and more in general, the common denominator of all my research, are all those decision, coordination, and control problems that arise in large-scale complex infrastructures upon which the modern society is based. So a perfect example of such infrastructures is the modern power grid. We all know that in recent years, environmental concerns, sustainability concerns, and even more recently, geopolitical concerns motivated the quest for a novel power grid, in which the energy production, the energy transmission and distribution is more efficient, decentralized, and largely based on renewable energy sources, such as wind and solar. This transition is actually actively driven by countries that are willing to, for example, deregulate energy markets to achieve a more sustainable power grid. As a result, also, there is a growing interest from the industry side in developing smart energy services. So in a future deregulated energy market, also lower level prosumers, which are consumers with production and storage capabilities, are envisioned to actively participate. The resulting market leading problem, which is the problem of finding the optimal set points one day ahead in advance, can be cast as individually as optimization problems. In particular, each prosumer has a decision vector, which includes its flexible load, its storage, and its trading profiles with other prosumers. And its objective is to minimize the discomfort from shifting the load, plus a cost that comes from the grid usage, the cost of a profit of trading, and a cost coming from the degradation of its battery. At the same time, its decision must fulfill some constraints that are represented by the dynamics of the devices it uses, such as the batteries, and some, for example, some trading limits, and as well as to the grid limits itself. At the same time, there is going to be a central operator, usually the distributed network operator, that has an incentive signal that can steer in order to maintain the network outcome reliable, right? And if you notice here, the catch is that these are not just normal optimization problems, but the decisions of prosumers and network operators are coupled. They enter the optimization problems. So another classic example is the supply chain, which has recently faced some harsh difficulties. We can streamline the cooperation and conflicts that happen in the supply chain as the classic Nash-Carnot competition, in which manufacturer can decide upon some order rates and delivery rates, and their objective is to maximize the profit, minimize the cost for buying materials from suppliers, and everything has to live within the own system capacities. And also here, usually in these sort of competitions, there are some entanglements happening from the prices that couple the decisions of all the manufacturers. Okay, and another very important example happens in transportation systems, where you have travelers that share the same road network and have to decide, for example, travel time in order to minimize the departure time in order to minimize the total travel time in the system. And of course, the total travel time, again, is a function of the old congestion, which couples decisions. Okay, so these systems in general are very different in nature, but have some very, very interesting, important parallels. For example, they all consist of many self-interested decision makers that have local decision authority and preferences. The information in general is distributed, and in certain cases, privacy is a main concern. And most importantly, the aggregate behavior of the decision makers may lead the system to instability if uncontrolled. Think about power outages in power systems, the log jams that happen in supply chains, or traffic jams in transportation systems. Or if not to disruptive behavior, just inefficient behavior. It's also something that is highly undesirable for these systems. So a viewpoint that in the last decades has gained considerable momentum in several engineering disciplines is game theory. I like to use a quote from, I like to quote Roger Myerson here, Nobel for Economics in the early 2000s, if I'm not wrong, that defines game theory as the study of mathematical models of conflict and cooperation between intelligent and rational decision makers. So under the game-theoretic lenses, the challenges of these large-scale infrastructures find a common interpretation. So in particular, self-interested decision makers that share resources can be modeled as games with coupling constraints. The locality of information can be modeled using network theory. And a safe and efficient operation of these systems, where efficiency is intended both local and global, can be oftentimes modeled using certain classes of equilibria, and in particular, variational equilibria. Okay, so in this talk, I want to discuss first the most recent advances in computational methods to solve GNE seeking problems, or in other words, in algorithmic developments to learn equilibria in these large-scale interconnected games. After that, I want to build up on these results and show you how we can use these algorithms to design some dynamic feedback controllers to drive these dynamic systems to efficient equilibria in a dynamic way. And then I will draw some conclusive remarks. Okay, so let's start from the computational methods. So let's abstract the problem as much as we can. So let's consider generalized games over networks. So the setup is the following. We have n agents or players, and each agent has a decision or an action xi and an objective. The objective of each agent is to choose its local action xi to minimize a local cost function ji. That depends on the local decision, of course, and on the decision of the others. For those of you not familiar with this notation, this is essentially a stacked vector that collects all the decisions of the agents or players in the game, but the decision of player I. The decision is constrained by some local constraints that we denote as omega I, and by some coupling constraints. These coupling constraints are characterized by this set value function calligraphic xi that depends on the decisions of the others. A game is nothing more than the collection of these interdependent optimization problems. So the network part arises since there is an underlying pattern in which agents influence each other. And this defines the interference graph. Essentially, the interference graph defines how the agents influence each other costs or constraints. However, there is another network structure that has to be considered, which is the communication graph, which is the network that describes how the agents share the information. In general, these networks are different. And in this case, in the literature commonly, it's referred as partial decision information setting. Whenever these networks coincide, then we have the full decision information setting. And the second case, of course, is more complicated because imply that agents do not have the information necessary in order to take a proper decision, an informative decision about their actions. Okay, let's try to be more complete here. Consider the problem of market clearing that we've seen before. In that case, the agents are the prosumers. The decisions are their profiles of flexible load, generation, and storage over the next, usually 24 hours. The cost function is nothing more than the electricity bill. Local constraints are generation and storage limits of the devices, and the coupling constraints are the grid limits. And the game is essentially clearing the market. In that case, the interference graph is defined by the distribution network itself, so the physical network, whereas the communication graph in general can be different. For example, oftentimes in the literature, they consider agents able to trading energy among each other, and also that's also the only links that define information sharing. Okay, so a classic solution concept for generalized games is generalized Nash equilibria. Loosely speaking, is the situation in which everyone's decision is optimal, given what the others do. But oftentimes, this is not the most efficient solution of the game. And in fact, we will focus on a subclass of these equilibria that are known as variational generalized Nash equilibria. Variational generalized Nash equilibria correspond to a solution to a specific variational inequality problem or generalized equation, which is this one. Essentially, this guy here is known as pseudo-gradient map, and is a map that collects the local cost functions of the agents or players differentiated with respect to the local decisions only. And this guy here is known as normal cone operator, which is nothing more than the subdifferential of an indicator function. And in particular, is the indicator function of the global feasible set of the whole game. Okay, so a couple of things have to be said. So the set of variation generalized Nash equilibria is a subclass of generalized Nash equilibria. So for certain games, there might be there might not be variation GNE, but there are GNE. And also it's particularly desirable because it's socially fair. Or in other words, all the players are penalized in the same way in order to satisfy constraints that couple them. Okay. Another very interesting thing and positive thing about the variational GNE, which is connected to their interpretation of generalized equation, is that we can use a bunch of results from convex analysis and monotone operator theory in order to solve this problem and in turn find the solution of the game. So this is in fact, this approach in fact has gained a lot of momentum in the literature, not only of automatic control, but also operator theory. And essentially allows people to bypass usual game-theoretic dynamics in order to find game solutions via this operator-theoretic reformulation of the original game-theoretic problem. And in turn, using operator splitting methods, we can find fixed point dynamics that will eventually lead us to the desired equilibrium. Okay, this is just an example of the level of complexity that we can achieve in terms of algorithms coming from this approach. Here, of course, it's very complicated, but I can break it down for you. Essentially, it's an iterative method that at each step involves one update and one communication for each of the agents, right? And this is applied to the problem of market clearing that we have seen before. Essentially, here at each iteration, the prosumers send some grid use bits to the distribution network operator, and in turn the distribution network operator sends back some broadcast back to the whole distribution grid some grid prices, and so on and so forth, and it will eventually converge to a variational GNE of the market clearing game. And it turns out that this variational GNE is actually a very desirable situation. For example, it's operationally feasible. Here in the plot on the left side, you can see what happens when we do not consider coupling constraints in the problem. Here, the red lines here denote that the line capacity is exceeded, whereas when we consider coupling constraints, we are able to find solutions, equilibrium solutions that are reliable for the system. Another desirable configuration of this variational GNE is peak shaving. So essentially, it allows to remove power consumption or the load on the main grid during the peak hours to hours in which the grid is less congested. It turns out to be also economically efficient, and efficiency here is illustrated not as an aggregative quantity, but instead locally. We see that everybody is actually doing better off than what it would do when there is no coordination whatsoever in the market clearing problem. Another very important feature, but this is a feature of the algorithm itself, is that it's completely scalable. So no matter the amount of prosumers in the distribution grid, the convergence of the algorithm has the same speed. And this is true not only for the number of prosumers, but also for the connectivity level, so the amount of trading partners that each prosumer has. Right, so using this operator-theoretic framework, there has been a huge research thrust from the automatic control community towards designing efficient computational methods for games and for generalized games. So as a result, I would claim that these algorithms have reached an excellent level of maturity, to the point that an opportunity looms for using them to control. So namely, implementing them online in closed loop with physical systems. So in this case, a central research question is to study the stability and the robustness of such interconnections. Okay, some related works that I should mention before going on. People have studied very similar problems using continuous time flows. So considering agents with single or multi-integrator dynamics using passivity, or nonlinear dynamics via extremum seeking control. And same extremum seeking control in a sample database setting. But we will take a different avenue, and we will consider instead a framework that has gained quite a lot of momentum recently, that is known as feedback optimization. And I will spend the next couple of slides in essentially summarizing what feedback optimization is. So feedback optimization considers the problem of controlling a physical system here towards an optimal or a desirable steady state, where the steady state is representing implicitly using this optimization problem here. where U denotes the control input, while S denotes the steady state of this system here, which is a function, we call it H, of both the input and of an exogenous disturbance W. So to achieve this objective with minimal or virtually no information on the plant dynamics, the core idea of feedback of the feedback optimization paradigm is to close the loop with optimization algorithms that can be regarded in a sense as dynamic feedback controllers, and let the physics implementing them. Okay, in other words, in the optimization flow or the optimization algorithm, the evaluation of the steady state H is replaced by direct measurements taken from the physical system. Okay, so and under a timescale separation assumption, or in other words, the plant is much faster than the algorithm itself, it can be proven that this interconnection is not only stable, but is also robust with respect to both model uncertainties and also unmeasured disturbances W, which are the typical advantages of feedback controllers. So in recent years, this control paradigm has received an increasing research attention, both from the automatic control community, but also from more applied fields. So I took these slides from this paper here, this nice survey paper. And essentially here, most recent works in the areas are listed and categorized based on mathematical setup they consider, for example, linear or nonlinear plants dynamics, continuous or discrete time stability analysis, etc. So although this literature is quite comprehensive, there are still some important gaps, and some of which we will address momentarily. So we want to consider, first of all, sample data analysis, or in other words, consider the case in which algorithms are discrete, while the physical systems evolve in continuous time. So this is particularly important because choosing appropriate sampling time is fundamental to ensure stability of the interconnection. And second, we extend feedback optimization to consider also generalized equation objective that can model, among other things, also the game theoretic scenarios that I introduced before, right? Which the physical systems now consist of self-interested decision makers that are coupled through the physics. Okay, so this brings me to the second part of the talk, where I will introduce FES, or in other words, feedback equilibrium seeking. All right. Okay, so let me start by the mathematical setup we consider. Okay, so we consider a plant described by a nonlinear continuous time state space system here. So in the same spirit of the feedback optimization paradigm, we assume that we do not have access to the plant model and not even to the disturbance W. But the only thing we're able to is to measure the output Y. So on top of that, we also assume that we have standard regularity conditions for the dynamics, disturbances, and we assume that the plant is input to stay stable. So our objective, as before, is to design a feedback controller that drives the plant to efficient operating conditions. But now we encode the efficiency using generalized equations, where in particular F here is a continuously differentiable mapping, whereas B can be set valued and arbitrarily nasty. Okay, and S here is again is a steady state. Again, generalized equations of this kind can model a plethora of different useful objectives, such as optimization, as we introduced before, but also games, equilibria in non-cooperative games. So let me propose some concrete examples next. So consider the non-smooth optimization problem here, right? We're interested in minimizing a cost function that consists of two terms, one which is continuously differentiable, phi1, and one which is non-differentiable, possibly non-differentiable, probably lower semi-continuous and convex. So by substituting S here within the cost function above, we can equivalent cast this in this form, right? And now, by using Fermat's rule that dates back to the 17th century, so very old, we can equivalently model the optimality conditions of this optimization problem here as this generalized equation, where the mapping F now is this guy here, which is essentially the gradient of this composite cost function here. And this structure here comes from the chain rule. All right, so essentially the main message here that we can cast solution of the optimization problems as generalized equations. So very similarly for games. So in this case, we have a bunch of agents that we label with I that goes from 1 to n. And each agent has to choose a control action UI within a feasible set calligraphic UI. And each agent has also some decoupled local dynamics, nonlinear, arbitrarily bad of this form, which will lead also to some local steady state mappings, HI. Now, the local objective function in this case is JI and depends on both the local control input and also on this function H, which collects the steady state of the whole system now, right? So again, the cost functions in this case for games are coupled. The games again is characterized by these interdependent optimization problems, right? So Nash equilibrium, we have seen it before, is the condition in which everybody does the best given what the others do. And we can recast this as a generalized equation using the pseudo gradient mapping that we've seen before and the normal cone operator. Okay, so also games can be cast as generalized equations. Very good. Now, to solve the target parameterized GE, we consider a class of abstract iterative algorithms that we denote with T. All right, so the algorithm takes as argument the current control input, U, and the corresponding steady state, H of U. That depends also on the exogenous disturbance W. So in practice, however, the disturbance W is not measurable, and the steady state S is not available in Colossus form, right? So we do as the feedback optimization paradigm suggests. So we run the algorithm in parallel with the plant, and we replace the evaluation of H with measurements that are taken from the physical system. So the resulting sample data interconnection, which is illustrated here, couples the algorithm and the physical system, right? Okay, so let's get a little bit more concrete here. I want to present you some examples of suitable equilibrium seeking algorithms that we can use. In the case of optimization, for example, if we have the no-smooth optimization problem as before, we can just use proximal gradient methods, right? Proximal gradient methods that are described by this update T, right? So the new update is taken by taking the prox over the non-smooth term of the cost function applied on the descent direction of the smooth part. All right. We can get also more general than this. If we have a non-linear and non-convex optimization problem, the update can be just a sequential convex programming update when we linearize the problem at the current estimate. and we just run one convex optimization step. Okay, so the framework also hold more general things. For example, games. For example, for games, best response dynamics, in which all agents take the best response given what the others do, can be taken into account in our framework, but also pseudo gradient plays. Whereas instead of taking the best action given what the others do, you take just a small descent direction towards the best. And this is not the only thing that can be taken into account, but we can also consider more general algorithms for the generalized games, as the one that I discussed before. Okay, so it's important now to study the stability of this interconnection. And the main result that we obtain is the following. So under these conditions, so the algorithm is locally convergent and stable. The generalized equation is regular, so it's, loosely speaking, is a nice function of the parameters. And the plant is locally input to stay stable with respect to the measured disturbances. We can select a sampling period large enough such that the cyber-physical algorithm system interconnection is input to stay stable. Okay, to do that, we'll recast. We will essentially record to error coordinates and study how this system, the stability properties of the error coordinate systems. Okay, if we take some more strong assumptions, we can say something even more precise about this interconnection. For example, if you consider algorithms that are not only convergent and stable, but linearly convergent, then we can find some explicit stability bounds on the sampling time to make the interconnection input to stay stable. And the interesting fact is that it is under these assumptions, it is always possible to make this interconnection ISS by letting the sampling time be big enough. Right. Also, some interesting things. This is a small gain type condition, and checking this condition would require a lot of information about the system and the algorithm. However, implementing, which it's unreal in many cases to assume, but implementing this control paradigm also requires only the ability to measure the output of the system and to evaluate the algorithm. Okay, so let me discuss briefly some numerical examples. Okay, so consider the problem of steering a robotic swarms to an optimal coverage configuration. So we have n robotic agents, each of which is tasked with investigative SAS signals that we denote as R. While at the same time, they want to keep a certain level of connectivity among each other. All right, so we consider robotic agents described by this unicycle dynamics. And they're locally controlled using this controller here. Okay, so the physical system, namely the robotic agents, are stable, which is good. It's within our framework. Now, the local objective of each of these robotic agent is the following. So they want to minimize the distance from the source of the signal they're tasked to inspect, but at the same time, they want to keep a certain level of connectivity with the other agents. And of course, you can immediately see that these two objectives are contradicting each other in a sense, and also the decisions of these players are coupled together. Okay, so everything fits our framework, and that's perfect because we can design easily a feedback controller that is based on best responses. And and close the loop with this interconnected physical system and this best response inspired feedback controller that will eventually drive this network of robotic agents to an optimal deployment. So here, just you can see if I can make it start. Okay, there is a video that shows the source of signals in black moving across this Gauss plane, and the robotic agents that are these colored dots that adjust themselves in an optimal configuration in order to minimize their own objectives. There are a couple, of course. Here on top, on the right, you see how the tracking error of this configuration with respect to the Nash configuration evolves. And of course, it starts from a very high error and eventually will converge to something very close to zero. And on top of that, we also consider exogenous disturbances, which is nothing more than a wind field that disrupts the dynamics of the agents. And I will speed it up until the end. Eventually, you'll see that when the source of signals will reach the final configurations, also the agent will track the Nash equilibrium perfectly. Okay, another example that we considered is the temperature control problem in small buildings. So consider we have a 5-room single-story office building, which is large scale and has a very nonlinear model. So we want to control the temperature within these buildings by according to this control objective. So essentially here, this control objective says we want to minimize the effort, the control action, cost to bring the system within a comfort range of temperature, right? So the second part of the objective here is an exact penalization in L1 form of the distance of the current measured temperature of the building from the comfort range. Okay, the building has no linear dynamics and the model is large scale. So the state are a bunch of temperatures and other building elements. Our steering knobs, the control inputs are the air handling units and the radiators. And the external disturbances are the solar radiation, the ambient outdoor air temperature, the ground temperature, and the heat gains coming from the building occupants that access randomly the building. And what we can measure are the room's temperatures, the outside air, and the ground temperatures. Okay, everything turns out to fit our framework. Again, in this case, we don't have a game theoretic objective, but just an optimization objective, which is, however, very nonlinear. Very good. So by relying on our framework, we can design a non-convex. We can design, sorry, a sequential linear programming based controllers that eventually drive this system to the efficient steady state configuration. So we tested this controller on a model generated using the VRCM toolbox, which is a toolbox available online. And remarkably, we noticed that with respect to standard state-of-the-art, at least in the industry, hysteresis-based controllers that are controllers working in a very simple way, so with thresholds, we were able to achieve 55% reduction in constraint violation and 18% reduction in the energy cost. Okay, so this brings me to the conclusion. So we have seen, we have essentially presented FAS, which is a framework to design feedback controllers that guides complex dynamical systems to economic equilibria. The core idea of this approach is to use equilibrium seeking algorithms, also the most advanced ones that have been developed for games, and just using them in closed loop with very nonlinear and complex physical systems. So the main contribution of this work is to show that there is a certain degree of stability and robustness of this cyber-physical sample data interconnection. And we saw that it's possible to implement this control framework to very interesting problems, such as robotics for coordination or smart building controls. Well, what we're going to see next, or what are going to be a nice future research direction. So we would like to numerically validate this approach on a large scale game, for example, coming from supply chain. And another interesting thing would be to make this framework completely model free, or in other words, incorporating some online learning of the few parts of the model we need in order to implement these methods that are the so-called sensitivities. Another thing we're currently working on is to deploy the controller we developed for temperature control smart buildings on a real smart building, which is the ETH demonstrator. So the main things that I discussed during this talk can be found in these two papers. The first one is available, already available online. The second one will appear in the issue of August of the Control System magazine. Of course, I should absolutely acknowledge my amazing collaborators. First line mainly from ETH, the second line from elsewhere, TU Delft, Toronto University, Arizona State University, and of course also the amazing financial sponsors. That's it. Thanks a lot for taking the time to follow this talk, and of course I'll take any question.
Thank you, Giuseppe, for the great talk. Let's open the stage for questions. So if you have questions, you can simply unmute yourself and ask.
Giuseppe, thank you for the talk. We'll probably start unless anybody has a special urgency. But one thing was not clear to me is so you talk about two networks, right? So two graphs are describing the network. You know, one is the interaction and one is the communication, right?
Correct.
Are those fixed, or are they, or do they depend on the state or on some other factors?
So I mean,
or are they part of the decisions in a sense?
It's a case-dependent problem.
Mm-hmm.
So for certain examples or for certain games, these two things are inherently different. For example, think about aggregative games. Aggregative games are games in which the cost functions of each of the agents depends on some sort of aggregative quantity of the system. So in that specific case, the interaction graph, as here, as in this picture, will be complete. However, in general, the way the players can communicate is not necessarily a full network.
Yeah, so no, I was thinking that can you handle cases in which, for example, the interaction, I mean, either of those graphs is not okay. So these are not complete graphs, right? But the interaction depends on can be dynamically changing, right? So, for example, in the robot deployment case where you want to spread out but not too much, right? You still want to maintain connectivity. The set of neighbors, at least looking at your notation, seem to be fixed, right? So, but what if the set of neighbors depends on your position, for example, and your neighbor's position?
Yeah, I think it's an excellent question. So if the interaction graph varies over time, then you're looking at different games. In that case, I'm not sure what you can say about, you probably have to track the solution of a time varying game. So that usually in the literature, it's keep and fixed. It's keep fixed. Okay. The communication graph is different. The communication graph describes how information is shared among the players. And there are recent works, also less recent, 10 years old probably, works in the literature that describe how you can possibly find equilibria in case the communication graph varies over time. That's possible. And the assumptions on these methods are the usual one of distributed optimization. So the graph, for example, is connected at each step or repeatedly connected, meaning that every fixed time steps, the communication links describe a connected graphs. Emilio, does this answer?
Yeah, thank you. I'm asking because we are doing some of these things where we kind of like a look at how essentially like games can be represented as collection of smaller games, kind of like depending on how things evolve, right? So, and how the players that you actually interact with may change over time. But so that's why I'm asking. But yeah, thank you. It's interesting.
Yeah. In that case, I think the game essentially changes over time, and what you have to look at, it's probably how the solutions of these different games relate to each other. So it would seem to me a sort of time varying, to make an analogy to optimization, time varying optimization setup, where the optimization, or in this case the games, change over time.
Thank you, Giuseppe.
Any other question?
I have one. Giuseppe, can you hear me?
Yes, Saverio, can you hear?
Yeah. Well, we have already discussed this, but maybe you can clarify a little bit what are the assumptions on the games, because it's at the beginning you mentioned generalized games. So yes, exactly here the xi being a function of others, but I think later when you presented the iteration.
So the underlying assumptions on the games, I didn't discuss them here explicitly, but let's say in order to design algorithms, the classic assumption for games is the game map or the pseudo gradient map has some monotonicity property, either strongly monotone or monotone. Mm-hmm. It's very tough to go beyond that.
Do you have this slide when you introduce the iteration T, though? I think
I'll try to find
maybe a little bit further down the road here.
For games, let's see.
Yeah.
Is this one?
The one before. Try the one before.
Look, here there are some assumptions, right? So, for example, these assumptions give guarantees for the algorithm to have the properties that we need in order to say something about the cyber physical interconnection with the physical system. In this case, for just games without coupling constraints, having the mapping, the pseudo gradient strongly monotone ensures that best response dynamics are linearly convergent.
Yeah.
So this is one possible assumption that we can conjecture in order to get the properties of the algorithm that we want. But we can relax this, right? So for example, for if we use instead of best response dynamics gradient or pseudo gradient play, we can say, okay, the mapping F is cocoercive. Cocoercivity is a weaker assumption.
Yeah.
Is to make an analogy with optimization is as strong monotonicity stays to coercivity as strong convexity stays to convexity.
Yeah. Okay, thank you, Giuseppe.
You're welcome.
I have a question.
Edzard? Oh yeah, go ahead, Edzard.
Yes, on the slide, so it's a good time. U is the action space that you consider is a continuous space?
Yes.
So for discrete games, would the results somehow extend to, let's say, mixed policies, or is it not quite the same?
Probably, I'm not sure about this, but yes. So essentially, what we need in order to study stability and robustness of this cyber-physical interconnection between the algorithms and the physical systems are, among other things, certain good properties of the algorithms, such as linear convergence or convergence and stability. And to have that, we need, in turn, to have some nice properties of the game. So it's kind of hidden here, but yes, we need games with continuous action spaces such that we can design algorithms that converge linearly to an equilibria. I'm not aware of algorithms for finite action spaces games that converge linearly.
Yes, it's a difficult problem, I believe.
I'm not even sure we can define linear convergence for games with finite action space. So yeah. In short, no, we cannot consider games with finite action spaces.
But I'm wondering if considering mixed strategies is the same, or
I mean, mixed strategies are complex games, right? Because they're games with compact action spaces, and depending on the cost functions, but usually cost functions are mixed strategies are complex games. So yes, those are covered by this framework.
okay, but usually the best response is like a pure strategy. So I don't know if some of these things become very non-smooth.
I think you can generalize best responses to mixed strategies.
Yeah. Anyhow, we can discuss it offline.
Yeah.
And in any case, just to add, you're not jumping to the best response strategy. Like that's only the TI, but then the TI is convex combined, right? To get so the iteration. So if you, I think you have in the previous slide, the iteration uses the TI, but doesn't require you to jump to the pure best response, or the one before again. Okay, exactly here. So you could average it, right? It's not that you necessarily need to apply the best response, the only pure strategy, which is in the best response.
Yeah, I'm not totally sure about that. I think I have to think about it a little.
Other questions? Maybe I have a slight less technical ones, maybe related also to the first slides we show. So we saw a talk from Saverio a while ago about power grids. Then you also showed some applications in mobility. I know you're working in both of them. Can you tell us a bit, or you're planning to work on both of them? Can you tell us a bit what kind of problems are you thinking about in those domains? For instance, in the mobility case, what are the players trying to do, and how do these assumptions or how does this framework translate to that case? Sure.
So I have to start by saying that I'm definitely not an expert on the applications on the mobility side, but essentially let's say the common denominator of all these coordination problems is that you have self-interested decision makers in this case, the travelers that share common resources. And in this case, the resource is the transportation systems. And their cost functions or their payoff functions depend on the congestion of the system, right? So in a sense, they fit the framework of generalized games. So whenever you want to develop methods to find equilibrium solutions for these problems, so you can rely to the framework that we developed.
Okay. Okay, sounds good. Any other question?
Actually, I have a question, if I can.
Yeah, go.
So, thanks, Giuseppe, for the nice talk. I don't know if you can see me or not, but I wanted to ask, maybe I misunderstood that part, but so what is the level of feedback that, or knowledge about the game that the agents need to, or the central like planner needs to know in order to implement these methods, right? So do you require the gradients of the cost and full knowledge of the constraints, or this also kind of extends to maybe just knowing the cost for the realized actions and not maybe knowing the exact like gradient of it?
So typically, yes, you need to have a gradient oracle. Okay. In the let's say the most general case in which you still need gradient oracle is the case in which the decision variables upon which your cost function depend, you don't have access to those, so you have to estimate them in a certain sense. But yes, you know your own cost function and you have a gradient oracle. There are methods that try to go beyond that, and essentially are those based on extreme seeking control. Here I listed a few, in which what they would essentially do is to estimate the gradient via some via different techniques, right? So they have an oracle of their cost, and based on that, they try to estimate the gradient.
Okay. Okay, thanks.
All right. I want to thank you again, Giuseppe, for the great talk, and also you created a nice discussion. I think you left your coordinates in case people want to reach out, even though I think everyone here knows you. So yeah, feel free to reach out to Giuseppe for further discussions. Thank you very much. Thank you all for participating, and see you all in 2 weeks for the next Autonomy Talk. Bye.